Hello, everybody. It's Professor Rehse coming to you again. It is time for another one of our virtual Great Lakes Region and Tribal Nations DoD STEM K-12 learning sessions. This is November of 2024, so this is our BAASHKAAKODIN-GIIZIS, which is freezing moon in Ojibwe. Forgive the pronunciation if that was mispronounced. I did my best. Noviembre, Spanish, and November, English version of the learning session. So we are very, very thrilled to have all of you with us today. We have a bunch of really neat topics for you. So today I want to talk to you about something that's kind of near and dear to my heart as someone who teaches medical physics. So my name is Steve Rehse. I'm the professor of physics. I'm the head of the Department of Physics at the University of Windsor. And one of the things that I teach in our classes is medical physics. And one of the big applications of medical physics is the use of X-rays. So we're trying to understand what X-rays are and how they can be used. So I have a presentation for you today that's going to take us through all of the things we need to know. So let's just go ahead and take a look at that. I'm going to share my screen. I've got a short presentation to run through with you, and I hope by the end of this, we're going to learn some things. So here we are. I'm going to get a little laser pointer up on the screen. So what I want to take you through today is the XYZs of X-rays. So that's going to be our mission for today. So to understand all the bases of X-rays. And here are some really cool images of X-rays that I hope we can understand a little bit better by the end of this presentation. So let's just jump right into it. So the University of Windsor is actually right here. So it's nestled on a river right in between Windsor, Ontario, Canada, and Detroit, Michigan, United States. So very much sister cities and very good friends, all of us on this call, separated by a small body of water. And the University of Windsor is right here where this rotating star is. It's nestled under the Ambassador Bridge that connects these two great countries. And the University of Windsor actually sits on the traditional territory of the Three Fires Confederacy of the First Nations. This includes the Ojibwe, the Ottawa, and the Potawatomi. So we all respect the long-standing relationship with the First Nations people in this place in the 100-mile Windsor-Essex Peninsula and the Straits of Le Detroit of Detroit. And you can see this beautiful Detroit River here that I'm talking about. So very happy to have you all with us today. So I'm wondering, as you're watching this, how many of you have ever actually had an X-ray? It's an extremely common medical application. So even though a lot of you on this call might be quite young, it's entirely possible that you've been through one of the procedures that has been pictured on the screen here. Perhaps you've gone to a dentist to get a dental X-ray. Perhaps you've had a jammed finger from playing Little League Baseball and the ball hit you on the finger and you got to go have an X-ray to go take a look inside of it. Or maybe somehow your tummy hurts and you just can't figure out what's going on, so you're going to look inside. So this is an extremely common application. So I bet it's a lot of you out there who have actually had an X-ray. So it's really worth it to learn a little bit more about it, just so the next time it happens, you're going to completely understand what's going on and you won't be scared at all. And you're going to realize this is a super useful tool. So as I just said, they are super useful in medicine. One of the big applications is going to be at the dentist. So even if you've been fortunate enough to never had any kind of injury where you've broken a finger or a bone or anything, you're probably going to be x-rayed at least once a year. So it'd be very, very common for a dentist to put an x-ray machine up against the side of your jaw, and they're going to use this to look inside. The dentist can only see the surface, but the x-rays look inside your mouth, and they're going to be looking for signs of cavities, tooth decay, carious tissue, gum disease down here below where they can't see. And they should really be doing that about once a year just to keep track of what's going on underneath the gum line in areas they can't see. So you're probably going to encounter x-rays in this situation for sure. Of course, as I said, if you're unlucky enough to had some sort of a broken bone or a finger, you're going to have to go in and the doctor's going to order some x-ray images taken just so they can see exactly what the extent of that damage was. This actually looks pretty painful. But it's not just these broken bones and teeth. We can also use x-rays to look at things like the blood vessels in your heart. So probably not so common for a lot of you on this call, but for those of us older presenters who are here, you're going to maybe have a doctor who wants to look inside your heart, and they really want to see what these coronary arteries are all doing. So the coronary arteries are these blood vessels that flow through the heart and on the surface of the heart. And if you want to know how well they're working, you need to use x-ray technology to do that. We'll talk about that a little bit today as well. And then sometimes It's actually even useful for seeing things in your brain. So we don't have any other way other than X-rays and magnetic resonance imaging to look inside the brain. There's no way a doctor can look through any opening, your eyes or your ears, and see what's going on inside the brain. So these X-rays that penetrate through the brain allow us to really look inside of you. So a super useful technology that's almost not really doable any other way. It's not just medical applications X-rays are useful for, though. Border crossing, I just showed you. Windsor is a border city, border between Windsor and Detroit, and so there's X-ray technology at the border. So you might see this as you're driving through borders in your vehicle. You can look, and these are large X-ray machines that shoot X-rays right through the car, and they're looking for things like this. They're looking for people who have contraband, illegal material, and they've hidden it somewhere away in the vehicle that the border guards can't see. Well, the X-rays go right through that, so they should have no problem seeing these hidden packages there. Another place you might see X-ray machines is, of course, at the airport. Anyone who's traveled through an airport knows this procedure of putting all your stuff inside these gray plastic bins, and the bins go into the X-ray machine, and then you have a security guard there who's like looking at X-ray images that go right through everything, and they can see exactly what you're carrying onto the plane. I just traveled recently a couple months ago, and you might see these newer, very high-tech looking X-ray machines that are coming online. The technology is getting much, much better at really identifying everything that you're carrying with you as you walk through an airport. So you're for sure going to see X-ray in these areas as well. So X-rays are super, super useful. Let's just dig into where X-rays kind of come from and how were they discovered. So X-rays were discovered in November 1895. So this is something that really burst onto the scene very suddenly. So in November 1895, a German physicist named Wilhelm Röntgen was conducting an experiment in his lab, and he was using an evacuated vacuum tube that shoots electrons through it. And here's a picture of such a tube. We call this a Röntgen tube now. I do not believe this is called a Röntgen tube at the time that Röntgen was using it. I don't know exactly what he called it, but he was German anyway, so there probably was a German phrase for it. But in honor of the discovery that's going to come from using such a tube, we now call these things Röntgen tubes. So he was doing some experiments on something else, had nothing to do with X-rays, because X-rays were not known about at all. And as he was operating this apparatus, he noticed that photographic plates near his equipment had started to glow. This is very, very strange. So he thought, there's something going on here. Here's a picture of Röntgen in 1896. So this is what Röntgen looked like. And so we credit the discovery of X-rays to Röntgen, who doing the experiments, who happened to be a good physicist, and he noticed something was going on and started to do some experiments into this phenomena. What Röntgen noticed is that when he was operating this tube, the glow of the plates nearby was due to some kind of beams being emitted by the tube. It's very, very strange. He couldn't see these beams. He couldn't see them. He couldn't smell them or feel them. But certainly these photographic plates were responding to the presence of this beam. And he did some experiments, and then he was very surprised to find that those beams could penetrate right through solid objects. I think he was putting these plates inside locked wooden boxes and even being enclosed inside a wooden box. Nope. They were still seeing the presence of these beams. So these are almost like some kind of magic beams coming out of that tube. He didn't know what they were. So he referred to this new form of radiation, which is what we call waves of something coming out of this tube. He called it X radiation. And he called it that because X is very commonly used in mathematics and physics to represent an unknown quantity. So, for example, a famous show on Fox television was The X-Files, right? And the X-Files were unknown, files of crimes and mysteries that were just unknown or unexplainable. And that's what X is always kind of denoted in science. So he called it X radiation. And he did a series of initial experiments, and as scientists do, he announced this to the world as quickly as he could. So that discovery was in 1895. On January 5th, 1896, just a few months later, Röntgen published his results, including a now very famous picture of his wife's hand. So his wife was Anna Röntgen. Here's a photograph of Anna, and here's the image that Röntgen took of Anna's hand and her wearing her rings, and he published this in the paper in which he announced the discovery of this mysterious new X radiation. And you can see, even though this is well over 100 years ago, a pretty good X-ray image. All of the bones in her hand are visible. It's very clear that the rings do not allow the X-rays to go through. And something very, very important was being announced in this paper. The world recognized that right away. This was something fundamentally new, very important, and very useful. And in fact, Röntgen's discovery of the X-rays earned him the first Nobel Prize for Physics in 1901. That's a little about 5 years later. So a very quick recognition of this very important discovery. Now here we are, roughly 120 years later, and we now know what X-rays are. They're no longer X for unknown. We have no clue what they are. We know what X-rays are. X-rays are a form of what we call electromagnetic radiation. And in that way, they are similar to light, which is another form of electromagnetic radiation. So electromagnetic radiation is a phenomena that occurs in nature, very, very common phenomena, where waves of energy, which are invisible, can propagate through our universe. And the properties of these waves as they propagate through the universe are kind of given by the energy of those waves. And then we perceive them and interact with them in different waves. There are very, very low energy waves that are like radio waves. So every once in a while, I'm in my car, click the button, I turn on the radio, and I'm picking up radio broadcasts, most of the time from Detroit, sometimes here in Windsor. Those waves are permeating through us all the time. They're completely safe, and they carry information in the form of radios. If you increase the energy a little bit, you can form what are called microwaves. Microwaves are actually what are cooking the food inside your microwave oven. That's why we call the microwave a microwave. It uses a form of electromagnetic radiation called microwaves. And they're very useful at heating up things that contain water. You increase the energy a little bit, you get to something called infrared radiation. This is a picture of remote control right here. So a lot or most remote controls actually have a small infrared LED on the end. And when you're pressing the button, it's actually sending out a beam of invisible radiation from your remote to whatever you're operating to make it change the channels, for example. But that's why remote controls don't work if you have your feet propped up on the coffee table in front of you. You can't shoot your remote control through your feet because this is a beam of radiation, and that infrared radiation is not very high energy. It doesn't go through your feet. Then there's visible light, which of course you know all the colors of the rainbow all around us is what we call light. That's the visible spectrum of electromagnetic radiation. As you add the energy, you get to ultraviolet light. Now we're getting into stuff that can be dangerous. Everything up here is so energetic, it gets to be very penetrating and a little bit dangerous for humans. You know that ultraviolet light can be dangerous because this is what gives you sunburns. And enough sunburns, enough exposure to ultraviolet radiation can actually generate skin cancers. So starting to get dangerous. If you add even more energy, you get the X-rays, okay? So X-rays are just a form of electromagnetic radiation, but with a lot of energy. The X-rays have way more energy than the light from a light bulb, and they have even way more energy than the UV light that gives you a sunburn. So these are just very, very energetic waves of X-ray radiation. And we're going to use the energy of those waves to do some really, really useful things for us. So what makes them useful is that they're so energetic, they can penetrate right through most materials. So it's that penetrating power that gives them their utility, their usefulness. It can go through things like wood, no problem. Thin metals, no problem. Concrete, yep, easily. And especially the soft stuff that makes up you. Our tissue is mostly kind of watery cellular tissue. X-rays go through that stuff really, really easy, no problem. There's a few things that lead doesn't, X-rays don't go through very well, and one of those is lead. One of the best materials used to stop X-rays is actually lead. So here's a picture of a coiled up lead sheeting, and then here's some interlocking lead bricks you can make to build a lead wall. Lead is really good at stopping X-rays. So it's super useful that we know that, because if we want to use X-rays as a useful tool, we also want a way to stop them and make sure the X-rays don't go where we don't want them to go. So if you go to a doctor or dentist, you might very well see the doctor, the dentist, or even a technician wearing something called a lead apron. So here's a photograph here of two technicians, and they're wearing this thing that looks like a cooking apron, but this is a lead apron. This is a quite heavy thing. Inside are some thin sheets of lead that protects them from the exposure of the x-rays. It goes up around the neck because they're trying to protect the thyroid. And this means if the x-rays are bouncing around the room, the x-rays cannot get through this lead apron, and everything underneath here is not exposed to the x-rays. If you go to a dentist, oftentimes they will drape a lead apron over you. So here's a picture of a woman getting a head x-ray, and she's in the machine, and you can see this blue apron they've draped over her shoulders. And this just keeps the x-rays, which you want to go through her head and jaw area, but you don't want the x-rays anywhere near anything else in her body because they don't need to be there. So you would commonly wear that type of apron. So if you ever go to the dentist and they lay that on there, you'll know it's lead because you'll feel how heavy it is. It actually feels kind of nice sometimes. I learned something new while I was putting this talk together. I was looking for a good image. So here's a very common image. This might be you next time you go to the dentist. So here's the dental hygienist or technician. She's wearing her pink lead apron right here. She's positioning the x-ray unit near the side of the patient's face, and the patient is wearing this lead apron right here. They just drape it over you and just make sure the x-rays don't go anywhere within your body. And as I was kind of learning a little more about this, I learned something really interesting and new. As of about 2024, the American Dental Association, the American Association of Physicists in Medicine, and the American College of Radiology have all concluded that the use of patient-led aprons during routine dental x-rays should be discontinued. It's not needed at all for patient safety. It turns out that the x-ray dose that you need to deliver for dental x-rays is really small. The detectors are so good that you really don't need very many x-rays at all, that the presence of that lead shielding is not needed at all for patient safety. And they in fact concluded that sometimes they actually can be detrimental to forming a good x-ray, because if they're not placed properly, they can get in the way. And then you actually need to maybe deliver more than one x-ray, and then you've actually increased the dose for very little benefit at all. So what these three professional societies have concluded is these aprons are really not used or needed for routine dental x-rays. However, you're probably going to be wearing them at the dentist for a while. So I do not suggest the next time you go get an x-ray at the dentist and they try to put one of these things on you that you say, oh, well, Professor Rehse said we don't need these anymore, so I'm not going to wear it. I wouldn't suggest doing that. Every dental office is going to have their own protocols. They have their ways of doing things. And so things sometimes change very slowly when it comes to safety. So I'm guessing they're going to keep using them for a while because this is a pretty new recommendation from these societies. But that just tells you, I just wanted to share this with you because it tells you really how safe they are. You don't even need the lead apron. They're that safe. So if they put the lead apron on top of you, you're even like doubly safe. So absolutely do not worry about these x-rays at all. They're very, very safe. When you get an x-ray, you're not going to feel anything. You're not going to see anything. You're not going to taste or smell anything. So it's completely painless. Very, very easy to do, but very useful, powerful scan that those dentists and doctors are going to be doing for you. So what makes x-rays useful? So I already said, so these x-rays are super penetrating, they go through stuff. Well, that's useful, but that's not actually what makes them useful. The key utility of the x-rays is they don't pass through all materials the same. That's the big thing. If you just had a ray that went through you and just went through everything easily, then there would be no image of you. Okay, and that's just not so useful. That's not the key. The key is that they are absorbed preferentially by some materials. So here's a patient underneath an x-ray machine. The x-ray machine shoots the x-rays through you, and the soft, watery bits of you are not very likely to stop those x-rays. So those x-rays that go through the soft watery bits of you will come through the patient, and here they would go through the patient, and they're going to be detected on a film cassette or detector. So here's an x-ray technician loading a film cassette where the patient would be lying here. The x-rays are going to come from above, go through the patient. Whatever gets through the patient is read and recorded on here. And that's all of the soft bits of you, the x-rays will go through easily. But the dense, heavy parts of you, like bones especially, are very likely to stop them. So we call that a differential attenuation of the x-rays. That's what makes them useful, because if all the materials don't absorb the same, those x-rays are going to throw a shadow. And that's really what an x-ray image is. So let's talk about this for just a little bit. So these are images that, of course, you've all seen before. I have no doubt about that. And you would have called that an x-ray before, okay? So that is not really an x-ray. It is the shadow cast by the x-ray. So the x-ray is the wave of radiation that comes down on the patient, And just like when you go out on a bright sunny day, you can do this anytime the sun is shining, and you look behind you, you'll see the shadow of you on the ground. This is just the shadow of the bones and hard, dense bits in your body being cast onto a detector. And so this is sometimes called a shadowgram, right? An X-ray image is really a shadowgram because it's the shadow of the X-rays. And then in the field of radiology, we more appropriately call these images radiographs. All right. So this thing that you say, oh, let me take a look at your X-ray, you shouldn't really call that an X-ray. The X-rays are the radiation that produce it. The image that is then formed is called a radiograph. Graph is like the word for image, and it's formed by X-rays. So we call them radiographs. And what's interesting about radiographs is they're what we call in the imaging field negative images. A negative image means that regions where no X-rays hit are bright, white, and regions where many X-rays hit are dark or black. This is the opposite of like a photographic image. So if you take a picture of something that's bright, usually where a lot of things hit, that lights up very bright in your image, right? And just take a picture of the dark sky. The star is bright and you'll see a bright white spot, and then where the sky is dark, you'll see a dark black spot behind it. X-ray images, the radiographs, are opposites of that. That's why we call them a negative image. Where nothing hits is bright white, and where many things hit, it's dark. So where the bone is, no X-rays were hitting, and the shadow was very deep. That's a white image. And then between, like right in between these two leg bones, you'll see it's quite dark here. That's where the X-rays penetrated through very easily, and so cast almost no shadow in the radiograph. So that's what we call a negative image. But some radiographs are actually positive images. They don't all have to be negative. The reason that those images were negative was due to the photographic film and the emulsions that were initially used to detect X-ray radiation. Digital radiographs nowadays, so here's a digital radiograph. This is called a C-arm X-ray machine, probably used for angiography, looking inside your heart. This is going to form a digital image of the X-ray radiograph, and digital radiographs are usually positive images. So in a positive images, the regions where no X-rays hit or dark. So now you're seeing the places where the X-rays go through easily are going to be very bright. So in here, you're seeing the lung tissue. X-rays penetrate easily through lung tissue, so it's kind of bright. Here you're seeing the rib cage and then the vertebrae, a little bit darker because the X-rays don't go through the bones as easily. And then you're picking up the metal, bits of metal where the X-rays really don't go through very much at all. And I'm wondering if you guys know what we're looking at right here. These are probably going to be pacemaker leads implanted inside the heart. Note the heart is not really visible at all, but you've got these very intense metal leads in there. And so that's a dark negative images. And sometimes you want to make use of this negative image to form something called an angiograph. Okay, so graph is again image. Anything with the prefix angio means something to do with your circulatory system. So an image where you're trying to take a picture of the circulatory system, which are your blood vessels, the arteries and veins, these are called angiographs. So an angiograph is also usually a positive image. The regions where no X-rays hit are dark. And as you see here, so you're seeing this is probably, you know, one of the major arteries, the carotid artery probably going up to your brain. And then you can see this beautiful, exquisite network of arteries that are feeding blood to every part of your brain. And here's a cool image on the right. This is a real-time image of what? The coronary arteries. So this is a cardiologist who's injecting what we call a contrast agent into the bloodstream. And both of these images, this here and here, where the blood is present, is very, very dark. Ordinarily, blood would not absorb X-rays at all, but in both of these angiographs, the physician or radiologist has injected a contrast agent right into the bloodstream, and that contrast agent has some types of metals in it that absorb X-rays really well. And so because they quickly permeate through your blood flow, then everywhere where there's a blood vessel becomes dark. And this animated GIF over here on the right, you can actually see the injection of the agent. This is some sort of stent device up in the upper left-hand corner that they've inserted into the heart, into the coronary arteries. And you can see the arteries kind of go away and get very light. And then you can see the moment they push the contrast agent, you can actually see the contrast agent flowing through all the vessels of the heart. And of course, it quickly clears away because your blood is pumping quite quickly. And so that contrast agent clears itself, but they're going to be snapping angiographs while those contrast agents are going through the heart. So that's a very, very useful application of X-ray radiography. They're great. They're very useful tools, but there's probably one really big problem with X-ray radiographs. As useful as they are, they have one big flaw, and the problem with that is there's actually no depth perception. So take a look at this X-ray of a human head. Right? So there's no depth perception. What I mean by that is as you look at this X-ray radiograph of the skull, let me ask you, are you looking at this from the nose that is in this image of the X-ray? Is the nose pointing out at us? Or are we looking at this radiograph from the back of the head and the nose is on the other side of the image? You can't tell from this image. There is no three-dimensional information in this image at all. And so say the doctor found some kind of a spot. Maybe they were looking for something inside your brain and they saw a spot like located right there. How would they know if that spot is at the front of your head or at the back of your head? There's no way to know. There's no depth information in an X-ray radiograph, which is a two-dimensional image always. So while you can tell something's there, you really don't know where it is. And so you would like that image to be way more useful. So that's one of the biggest problems. So a good question is, can we make this, which is a pretty good two-dimensional image, into something more useful, something that looks like this, a beautiful, what looks like a 3D picture of the skull? Or here's something here where, again, this is a 3D image of the skull, but I'm rotating it around. So maybe you'd be able to tell if something's on the right side or the left side. Or maybe we can even break this skull up into individual slices and kind of look through individual slices to see where in the body these things are located. So could we make this into this? Can we make a 3D X-ray radiograph? Yeah, for sure we can. There are such things as 3D X-ray radiographs, and we call that a CT scan. Sometimes people colloquially call that a CAT scan, but you really shouldn't call it a CAT scan. This is an older terminology. When I was a boy growing up, they called these radiographs CAT scans, and people still do. They'll still call them CAT scans, but the proper appropriate medical term for that is a CT scan. So the CT scan is taken out of a CT unit. So this is a CT scanner. The CT scanner it's an X-ray tube. So just now, the first thing that you've learned, I hope, well, maybe not the first thing, but one of the things I hope you learn out of this is when people say I'm getting a CT scan, that's an X-ray. I don't even think a lot of people know that. CT scans are just X-rays, kind of like everything else, but we do something very special. So this is a CT scanning machine. It has an X-ray tube, just like any other X-ray tube. The patient lays in the middle, so you're going to see this donut-shaped ring all the time you get a CT scanner. The X-ray tube's on one side. You have a whole bank of detectors on the other side, and you, the patient, lay in the middle. You lay on something called the couch, and you lay on the couch, and the couch will feed you slowly into this CT machine. If you took the cover off the CT machine, this is what you see. The magic of CT comes from the fact that the X-ray tube is actually spinning around you. It spins around you about 3 times a second, something like that. And it's taking X-ray radiographs of you the entire time it's spinning around, and the entire time it's feeding you through very, very slowly. So that's the key to a CT scanner. So when you do this, this is called CT, which stands for computed tomography. So computed tomography means by turning the X-ray beam into a thin slice, and usually when I describe this in my class, I call it like, just imagine a pizza slice. It's a wedge-shaped pizza slice of X-rays. It goes through you, and then we rotate the source around you. And by rotating the X-ray source around you, we can actually take slices of X-ray radiographs. And it's a lot like taking slices of a bread. So I like this illustration down here. If you've ever had a loaf of sliced bread, right, one slice pops out. I'm just taking one slice out through the patient. And here is one slice cut through the patient. And you can imagine many, 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 many slices piled up. And that's actually where this word tomography comes from. Tomos is the Greek word for slice. So any tomographic image is an image where we've taken slices of you, and then you can compile all those slices together. And that's what we do. The slices are taken individually, but then you pile all the slices together. So just like one slice of bread, when it's piled all together, forms a loaf of bread, one slice of a CT image, when piled all together, allows a computer to construct a fully 3D model of what's inside of you. So here in this animation, you can just see we're scrolling through all those different slices that have been taken through the brain and the skull. Or if you want, you could have the computer put all those slices together and not be looking at them one at a time. Can I kind of look at them all at once? And then that generates a pseudo 3D image. I don't call this a full 3D image because I'm looking at it on a 2D monitor. It's still 2D, but computers are very good at shading things to give a representation of 3D, which still is a way better image than that flat 2D X-ray radiograph that we were looking at before. So the CT scanner is one of the most useful, one of the most powerful medical imaging technologies that we have. It's a really common, useful tool, very good for looking inside, and almost any medical operation today that's of any serious significance is going to go order some sort of CT scan. It's just so useful to be able to look inside the body. The contrast is wonderful. You can see very small things, and it really is like giving a physician X-ray image, X-ray vision, where they can look inside of you and see the smallest problem and know exactly where in your body it's located. So a super important, super cool piece of medical technology. So that's kind of where I wanted to finish up. Those are the X-rays, XYZs of X-rays. I hope you've learned a lot about it. And I thought, since it's November after all, maybe shall we end this presentation on the XYZs of X-rays with a joke? Why not? Let's go ahead and do it. A little bit of humor. And as I was always told, probably a very little bit of humor. But let's try it nonetheless. So the joke is, what did the doctor say to the old lady who was worried that her doggie had accidentally swallowed her pet cat? Here he is looking down the doggie's throat. Nope, no sign of your kitten, ma'am. But to be absolutely certain, we better perform a CAT scan. Ugh. Like I said, very, very little humor, but I don't know. It makes me laugh when I see it. So thank you all very much for your attention. Thanks for spending a little bit of time with us today. I hope you learned something about X-rays, X-ray radiographs, CT scanning. I think you guys are going to see this at some point going forward in your life. So the next time that happens, I think you're going to have a way better understanding of what exactly is going on in that test. So I hope you appreciated this talk. I hope you appreciated spending time with me. I know I appreciated spending time with you all. So that's enough for today. Thanks a lot, everyone. Hope you have a great one. Bye.